In this video, we discuss linearization, increments, and differentials for functions of one variable. It's all based on this idea of using a tangent line as an approximation to the function. So sometimes we'll use this terminology, the linearization of y equals f of x at x equals x naught. It's just a tangent line. So y is equal to the y value at x naught plus the slope at x naught times x minus x naught. Remember, the slope at x naught is change in y divided by change in x. And then we're multiplying by change in x, so that's giving us a change in y. If we take that change in y and we add the original y value, we'll get the new y value. Now, rather than using the notation y equals this expression where this is a number and this is a number and this is a number, sometimes instead of writing y, we write L of x, where L represents the linearization of y equals f of x, and we'll write it that way. So it's just some terminology. Now, in this section, we're going to use some notation that bothers me a little bit, but that's okay. It's pretty standard. It's in pretty much all of the textbooks. So let's say you've got a function y equals f of x, and then you find the tangent line approximation or linearization of y equals f of x at x equals x naught. So I've got this tangent line, and it's approximating the function. Now, if I stay close to x naught, that tangent line and the function itself are almost, they almost coincide. If we zoom in a lot at this particular location, the difference between the black curve and the pink line is almost indistinguishable. But if I take a small step away from x naught to, say, x naught plus delta x, well, then there's actually a difference between the change in y, the actual change in y, which is the y value at the, or the new y value minus the original y value. And we call that delta y, or the increment of y. And then the expected change in y using the tangent line approximation. And the notation that we use for that is dy equals the derivative evaluated at x naught. So we're talking about a particular number here for that particular value of x naught times dx. Now, the thing that bothers me about this is that in this section and similar sections in Calculus 3, we are saying that x naught and delta x are interchangeable. Or excuse me, not x naught and delta x and dx are interchangeable. So these are both representing a small change in x, and we're going to say that they're the same thing. Now, typically we wouldn't say that with dx. This is actually an infinitesimal, so it's like an infinitely small distance in the x direction. So this is very, very, very close to zero. And this is a small positive, or well, it's actually not a small positive number, a small non-zero number. In this section and the similar section in Calculus 3, we're going to treat the dx and the delta x as if they're the same. So dx is a small change in x, and delta x is the same small change in x. Now, the differential of y is defined to be dy, or is notated dy, and that's equal to the derivative of the function times dx. Now, this is a definition. We're just taking that derivative function and we're multiplying by dx, and we're calling that the differential. It's just notation. And the increment of y is denoted by delta y. It's the actual change in y as x changes from x naught to x naught plus delta x. So we say, okay, well, what is the change in y? It's the new y value minus the original y value, and that's the actual change. Now, if I take my differential and I evaluate this derivative at x equals x naught, and I substitute a particular value for dx, so that dx and delta x, it's a small change in x. If I substitute that change in x here, and I substitute that x naught value here, and multiply those together, this gives us a dy that can be interpreted geometrically. This dy is this change in y. It's the change in y using the tangent line as an approximation to the function as x goes from x naught to x naught plus dx, or x naught plus delta x. Because again, we're using the delta x, or thinking of the delta x and dx as interchangeable. So we're going to use this terminology in a couple of different types of problems, or a few different types of problems. We'll use this when comparing the actual change in y to the expected change in y at a particular x value. That's the expected change, again, using the linearization or the tangent line as an approximation to the function. We'll use this when we're computing propagated error, and we'll use this when estimating values of, like, say, square root or a cube root or something like that without a calculator. So here's an example. This is very typical for a problem, a quiz problem over this material in our course. So let's say our y value is 3 minus x to the fifth, and our delta x and dx are 0.01. We might be asked to compute the differential of y. dy is just the derivative of y with respect to x times dx. And this is where y is equal to f of x. In this case, y is equal to 3 minus x to the fifth. So the derivative of this is the derivative of 3, which is 0, minus the derivative of x to the fifth. So we get negative 5 times x to the fourth using the power rule. So we bring the 5 down, multiply by x to the 1 less power, and multiply by dx. That's dy. It's very simple. It's just the derivative times dx. We're going to use this again when we learn about anti-differentiation later with a technique called U substitution. So dy is just the derivative times dx. And we call that the differential of y. Now we're asked to find the actual change in y as x changes from 2 to 2.01. That's delta y. So we're going to evaluate f at 2.01, and then we evaluate f at 2, and then we just subtract. So f evaluated at 2.01 is just 3 minus 2.01 to the fifth, and then we're subtracting f evaluated at 2, so that's 3 minus 2 to the fifth. And if we distribute that negative, the 3's reduce, and so we end up with 2 to the fifth minus 2.01 to the fifth. And I actually don't know what that is without a calculator, so I'm going to use a calculator to find that. And this is just a pretty standard calculator on the phone. It doesn't even have exponents on it. I'm going to do 2.01 times 2.01 times 2.01 times 2.01 times 2.01 equals, and I get 32.808 approximately. Plus 2 to the fifth, which is 32. And so my actual change in y is approximately negative 0.808. So it looks like my y values are actually decreasing. And as I'm going from x equals 2 to x equals 2.01, my y values are decreasing by approximately negative 0.81. So we computed that. And then we're asked to find the expected change in y using the tangent line approximation as x changes from 2 to 2.01. Well, in that case, delta x and dx are the same. They are given by the final x value minus the initial x value. So we've got a final x value of 2.01, and we're going to subtract the initial x value of 2. So our change in x is 0.01, and the expected change in y is given by dy evaluated at x equals x naught and that corresponding value of dx. Now, f prime of x naught, and x naught is x initial. So we're starting at that base point of x equals 2. So we're going to have f prime of 2, and we'll multiply by dx. Well, f prime of 2 is that negative 5 times x to the fourth evaluated at 2. And then we're going to take that, we're going to multiply by that 0.01. And that's going to be an approximation of the change in y using the tangent line as an approximation. So it's an expected change in y using that tangent line. So I have -5 times 2 to the 4th. 2 to the 4th is 16. So we'll have 5 times 16, 80 times 0.01, and I get 0.8. So we see that the actual change in y is -0.808 approximately, and the expected change in y using the tangent line approximation is 0.8. So the difference between those is 0.008. So this approximation is accurate, at least to that first decimal place, and that second decimal place might be off by 1. So we see that the tangent line is actually an excellent approximation. Now we're asked to illustrate B and C graphically. This is difficult to do because 2 and 2.01 are so close to each other, but you can do this on a calculator. You can also do it on paper, but usually your graph is not to scale. So if I try to do this on paper, I say, okay, I've got y equals x to the 5th, which kind of looks like x cubed. It's just a little bit flatter at the origin. Between -1 and 1, if I raise a fraction to the 5th power, it's going to be smaller than if I raised a fraction to the 3rd power, if I just had a fraction, the fractions themselves. So that's why it makes it a little bit flatter between -1 and 1. If we're subtracting that, that's gonna flip the values, and then we're gonna add 3 to that. So our graph roughly looks like this. When x is equal to -1, we have -1 to the 5th, which is -1. 3 minus -1 is 4. And then at x equals 1, we'll have 3 minus 1, which is 2. Again, it's very flat in between those two values. And then at x equals 2, the value is 32 minus 2, or 3 minus 2 to the 5th, excuse me. 2 to the 5th is 32, so we have 3 minus 32, which is -29. My goodness. That's probably why I shouldn't have used the 5th power. So say not to scale, -29. We're gonna look something like this. Okay, and then at that location, we will draw a tangent line. So I draw my tangent line here. It's a little bit difficult to see. See, my tangent line is going to roughly look like this at x equals 2, y equals -29. So something like that. And then the question is, well, how does the actual change in y as x goes from 2 to 2.01? So tiny, tiny distance in the x direction. How does that change and the actual change in y differ from the expected change in y? And there should be a negative sign there. Well, those are off by 0.008. Now it's a little bit difficult to see right here. So I'm going to illustrate this on Desmos.com. When we're on Desmos, it'll still be difficult to see, but if we keep zooming in and zooming in and zooming in, we might be able to see that difference. We might not. I'm not sure, but we'll try it. Okay, so this is what f of x equals 3 minus x to the 5th looks like. It's just that x to the 5th graph, it shifted up 3 units and then it was flipped. So typically this is what I would draw. And notice that between -1 and 1, it has sort of a flat spot there. And that's because if we take those fractions between -1 and 1 and we raise them to the 5th power, they're going to get even smaller. So it makes it sort of flatter. And we are actually interested in this function near x equals 2. So it's actually kind of far out. X equals 2 is way down here. Oops. At x equals 2 and y equals -29. So that's our function. It's our function and its corresponding function value at x equals 2. Now the derivative is easy enough to compute using the power rule. The derivative of 3 is 0. The derivative of x to the 5th is 5x to the 4th, and then we've got the negative there. So our derivative is -5x to the 4th. So the differential of y is denoted by dy, and that's just that derivative, -5x to the 4th times dx. If somebody asks you for the differential, all they want is this. They just want that derivative times dx. Now, if we want the actual change in y as x changes from 2 to 2.01, we just evaluate f at 2.01 and evaluate f at 2 and subtract. Visually, we might be interested in what the graph looks like or what that point looks like at 2.01. So there's a nearby point. Let's keep zooming in. So there's the function value at 2, and there's the function value at 2.01. And the change in those values is this this function value at 2.01 minus the function value at 2. So we get that -0.808 approximately. Then we're asked to find the expected change in y as x changes from 2 to 2.01 using the tangent line at x naught equals 2. The expected change in y using the tangent line approximation is that derivative evaluated at 2, which is that -5 times 2 to the 4th. And then we multiply by that change in x, which is 0.01. Then we get a -0.8. Now we can see that visually if we graph the tangent line at that location. It's a little bit difficult to see because it's so steep. And then we would want to try to differentiate between the tangent line and the function itself, but we can't. It's almost impossible. You can see a little bit of a difference. Maybe if I change my scale in the y direction, my y's are going between -29 and -30. So maybe we should say that our y's range from -29 or 28.9 to -29.5. No, 30. I need to go up to 29.81 at least. So we see that those two y values are, the difference between the two y values is that -0.808, but using the tangent line approximation, the difference is -0.8. It's kind of difficult to see given that tangent line. It might be easier to do this, to illustrate this using a larger step size and maybe a different base point where the graph isn't so steep. So let's modify the problem a little bit. So our differential of y is still the same, but maybe instead of using 2 and 2.01, we should use a different value for the function. Let's use x equals 0. Oh no, x equals 0, it's flat. Don't want to do that either. This is what the graph looks like. Maybe we'll use our base point of 2.5, or sorry, 0.5. So we'll say, let's say that what the actual change in y is as x changes from 0.5 to 1.5. So I've made my change in x actually really large. I've made my change in x equal to 1. Well then, the actual change in y would be f of 1.5 minus f of 0.5. So we'd have a difference of negative 7.5625. Now, if I'm interested in the function values at 0.5 and 1.5, I can plot those points. Here's my function value at 0.5. And let's look at the function value at 1.5 as well. Of course, our delta x and dx should be relatively small. I've got that. And then if I sketch the tangent line at x equals 0.5, this is what it looks like. Say, okay, well, the actual change in y was that negative 7.56, but the expected change in y is negative 5 times 1 or 0.5 to the 4th times 0.01, or actually times 1 because our dx is now 1. So we actually would only expect our y value to change by negative 0.31 units if we're using our tangent line as an approximation. We can see that if we evaluate the linearization at x equals 1.5. So I'll call this L of x now, rather than calling it y. We'll evaluate L at 1.5 as well. And so we say, okay, let's look at how much do we expect the y values to change? Well, if our x's go from 0.5 to 1.5, we would expect the y values to change by this 2.656 minus that 2.969, which gives us that negative 0.3125. But then we see that doesn't actually happen. The actual change in y is the difference between this y value and that y value, and it's huge. That's because our step size is so large. We're taking such a large step from x equals 0.5 to x equals 1.5 that we wouldn't expect this tangent line to be a very good approximation. You might say, okay, well, what can we do to improve the situation? Well, we could always move that second point closer. So instead of having a delta x or dx of 1, we could go from 0.5 to 0.6. Or let's just go from 0.5 to 1. Then we'll evaluate f at 1 and f at 0.5. And then our difference is this. Now the actual change in y is f of 1 minus f of 0.5. So we get this negative 0.9685. And the expected change in y is the difference between these two y values. So we see that the expected change in y is actually very small compared to the actual change in y, but that's because our slope is so large. Our slope is that negative 5 times x to the 4th. So we're, and our x value is between negative 1 and 1, so this is actually really small here. So as long as I'm choosing an x value between negative 1 and 1, that slope is going to be, well, that slope is going to be rather small in general at that particular location. But the corresponding change in the y values on the graph is related to that x to the 5th. I don't know how to explain it. Once I get outside of that interval from negative 1 to 1, I think the approximation would improve. So I'd say, okay, well, rather than using an x value, a base point between negative 1 and 1, maybe we should use x equals 1 as our base point. and then go from 1 to 1.5. So you can, but then it's just going to be a little bit more difficult to see the difference between the change in y, the actual change in y, which is the difference between this y value and this y value, and the expected change in y, which is that difference between this y value here and that y value. So this is your dy, which is not exactly the differential, but we use the same notation that we use when we use the differential. It's the derivative evaluated at the base point times that change in x. I mean, that's going to give us an expected change in y. That's very different from the actual change in y at that location. But if we took a smaller step, the approximation would improve. So we could go from 0.5 to 0.6. Now those 2 points are almost on top of each other. Then the difference between the y values, the actual change in y is negative 0.0465. And if we evaluate the linearization at 0.5, we can see it if we zoom in. The actual change in y is the difference between this y value and this y value. The expected change in y is the difference between this y value and that y value. I'm actually thinking of these vertical distances, a distance from the horizontal line, y equals f of 0.5. I'm like looking at the distance between that horizontal line and this y value and that horizontal line and this y value. The distance between the orange line and the purple line is the dy, that expected change in y using the tangent line approximation. And let's evaluate that. So I'd have negative 5 times 0.5 to the fourth times the change in x, which is 0.1. And I'm comparing that to the actual change in y. And so I get an expected change of negative 0.03125, and the actual change in y is negative 0.4651. Okay, I hope that sort of illustrates the concept. And I will reorganize this graph before I post it, so it makes a little bit more sense. And I actually like this version best, so I think I'll post it with the base point of 0.5 and our x naught plus dx or x naught plus delta x being 0.6, because then we actually see that the delta x or the delta y and the dy are very similar to each other at that point. Now we can also use these concepts with regard to error propagation. So if you measure some value, like the radius of a sphere, and then you use that radius to compute a volume, you'll come up with a volume, but if that measured value of the radius has some error in it, you're going to have a propagated error in the calculated value of the volume or the calculated value of the surface area. So in this problem, we're dealing with that type of error. We've got a sphere, and we're told its radius is 9 centimeters, and we have a possible error of 0.025 centimeters. So let's say our R naught is 9 centimeters, and that dr is plus or minus 0.025 centimeters. For us to approximate the maximum possible propagated error in computing the volume of the sphere, well, that requires a knowledge of the volume of a sphere, that formula. And we also, in part B, want to find approximate the maximum possible propagated error in computing the surface area of the sphere. I actually don't remember those formulas off the top of my head, but they are in the back cover of the calculus textbook. So we can look at that. So the volume and surface area of a sphere are listed right here. The volume is 4/3 pi r cubed. And the surface area is 4 pi r squared. Well, I'm actually not sure where I stopped recording. I know I stopped recording briefly to show you the formulas for the volume of the surface area or volume of a sphere and the surface area of a sphere. I wrote S subsurface area. What I meant was S subsphere for surface area of a sphere. Whoops. I looked those up on my on a formula sheet. Actually, I'll do that right now. I'll do it again. I might be doing it twice. There they are. This is in the back cover of the Larson Calculus Text 10th edition. And then we said, okay, let's compute dV and ds. dV is v prime of r dr. So you compute the derivative with respect to r of this. You just use the power rule and simplify, and you get this as your differential of v. Then you evaluate that at r naught equals 9 centimeters. So that's what you substitute for r. And your dr is that error in measuring r, that plus or minus 0.025 centimeters. So we'll use a calculator to compute that. And then for the surface area, we have this. So the ds, the differential of the surface area, is s prime of r times dr. So we compute the derivative of this using the power rule. Derivative of r squared is 2r, then you just multiply and we get that. And then we evaluate that at r naught equals 9 centimeters and dr equals 0.025 centimeters to get an expected change in surface area using the tangent line approximation to the function for surface area at r naught equals 9. Provided that our r value is changing from 9 to 9 plus or minus 0.025 centimeters. That's going to be the expected change in surface area. And this value, when we use the calculator to compute it, will be the expected change in volume. So let's do that on Desmos. So we have our volume and our surface area formulas and our volume and surface area differentials. And we're going to evaluate each of those at the base point with the particular value of r. So we have 4 times pi times r, which is 9 squared, and then we're going to multiply by dr, which is 0.025. And then here for the, and that's the expected change in volume at r equals 9 centimeters, provided that our error in measuring the radius equals 0.0 or is within 0.025. So this is the maximum possible propagated error. So that's 25.4469 approximately. And then here for the surface area, the expected change in surface area using that tangent line approximation at r equals 9, where our r value might be off by 0.025. Is this. So it's about 5.655 centimeters squared. And so we say, okay, are those large values? How can we tell if they're large values or not? Well, we can use what's called the relative error formula. Oops. And that's where you just take the differential and you divide by the calculated volume. So, or the differential that we've just computed, and we divide by that calculated amount. So we say, is 25.4469 centimeters cubed a lot when r equals 9 centimeters? Well, it just depends what v evaluated at 9 is. So v of 9 is actually 3,000. So you say, well, 25 isn't very much compared to 3,000. How much is it compared to 3,000? Well, you can compute this number divided by v of 9. And that is our relative error. And then if we take that ds, so that's this value, and then we divide it by the surface area at r equals 9, we get a relative error for that one as well. And you say, well, how big is that? If you want, you can multiply by 100 to get percent error. So that times 100, and we get a percent error of 0.83%. So it's less than 1%, so it's not very much at all. And here's our relative error. If we take that relative error for the surface area and we multiply by 100, we have 0.56%. So it's not very much at all again. And let's do that on paper. So we're gonna have the maximum error. Well, let's say maximum propagated error in computing whatever your quantity is, divided by the calculated value of V. So that's going to be our dV evaluated at R naught equals 9 centimeters and dr equals plus or minus 0.025 centimeters, divided by that V evaluated at 9 centimeters. And so what we get is approximately that 25.447 centimeters cubed divided by the volume at 9 centimeters. And I don't actually remember what that was. So it was approximately 3,053.628 centimeters cubed. And when we divide those, we get approximately 0.00833. And then we'll do the same thing with the surface area. The surface area at R equals 9 is that maximum propagated area, or error, excuse me, in computing S, divided by that calculated value of S, using that measured value of R. And so we have ds evaluated at R naught equals 9 centimeters and dr equals plus or minus 0.025 centimeters. And then we're dividing by S evaluated at 9. And it's approximately 5.655 centimeters squared divided by, just keep having to look at that screen, 1,017.876 centimeters squared. And if we divide those, get the relative error, we have approximately 0.00556. And the relative error is, or that's our relative error. So we say that change in volume, or that error in measuring the volume of that 25.4 centimeters cubed is not very much compared to that 3,053.628 centimeters cubed, the total volume. That's the relative error. And if we multiply by 100%, we have the percent error. So just move the decimal twice. So 0.833%. So that percent error is pretty small. So this is the relative error with the relative error using that propagated error for the surface area. And it's 0.00556. So we're saying that if we're off by 5.655 centimeters squared, and the total surface area is 1,017.876 centimeters squared. So that's not very much compared to this. How much is it? What's the comparison? Well, it's this much. If we multiply by 100%, we have 0.556%. So it's just a little bit more than 0.5% error. So that error is very small, but it's because that error in measuring the radius was very small. We're only off by potentially 0.025 centimeters, and our actual radius is much larger than that. So that is how we can use differentials to discuss and think about propagated error. But again, we're using, in both of these cases, we're thinking about propagated error when using the tangent line to these functions as an approximation to the functions themselves near a particular R value. So we're using, when we calculate dB and we find this expression, we're saying this is this value, this 25.4469 centimeters cubed, tells me the expected change in volume, or the expected error in volume, provided that we are at R equals 9 centimeters. We're using a tangent line approximation to this function, and our R values change by as much as 0.025 in either direction. If we have a plus or minus there, technically we should have a plus or minus there as well. And if we have a plus or minus there, we should have a plus or minus there as well. So again, these are tangent line approximations, and we want to keep that in mind as we interpret this. Now, the final type of problem that we have a tendency to see in this section involves approximating radicals. So sometimes they'll say, just approximate square root of 80 using tangent line approximations, or not tangent line approximations, using, let's say, differentials. Well, you say square root of 80 is very similar to the square root of 81, right? Square root of 81 is 9. So we could use x naught equals 81 as our base point. And then we'll let dx and delta x be equal to -1. So that x naught plus dx, or x naught plus delta x, is equal to 80. And then we'll use the function y equals f of x, where f of x is the square root of x, as the function of interest. So with that in mind, I can use the differential of this function evaluated at this point with this dx to approximate the square root of 80. Let's do that. We have dy is f prime of x times dx. So that's the derivative with respect to x of the square root of x, or x to the 1/2. So we get 1/2 x to the -1/2 dx. And that's our dy in general. That's our differential of y without evaluating at any points. If we want to, we could write that as 1/2 times 1 divided by the square root of x. And then if we multiply straight across, we've got 1 divided by 2 times the square root of x times dx. So we know that dy is equal to this, which is equal to that. And then we say, okay, well, what is the expected change in y using the tangent line approximation as x changes from 80 or 81 to 80? Well, in order to find that, we'll evaluate dy at x naught equals 81 and dx equals -1. So we'll have 1 divided by 2 times the square root of 81 times that dx, which is -1. So you have -1 divided by 2 times 9, which is -118. And I don't know what that is exactly, but I can use a calculator to approximate that. So 1 divided by 18 is at 0.556 approximately. So this is the expected change in y using the tangent line approximation. So what is the square root of 80? Well, that is the new y value. This is the function value that we're trying to approximate. It should be approximately equal to the original y value, the y value at x naught at 81, plus the change in y. So we could call this y naught if we wanted to. So we'll have square root of 81 plus the change. I think I missed a decimal point. There's supposed to be a 0 there. Let me look at my calculator again. Yep, there's a 0 there. So we've got 9 minus that value. Keep missing that 0. And then if we subtract, we have approximately 8.944 repeating. So I'm saying the square root of 80 is the original y value plus the change in y, which is approximately 8.944. Now, if I use my calculator, I can also find out what the square root of 80 actually is. So this is what we get. Here's our differential. If we evaluate that differential at x naught equals 81 and dx equals -1, we get this as our expected change in y using the tangent line approximation. And then the new y value should be the original y value, which was 9, plus that change. So we get 8.944 as our approximation. And we want to compare that to the actual value, square root of 80. And we see that they're very similar. If we wanted to, we could just subtract. Let's look at the absolute value of square root of 80 minus this expression here. And we see that the difference between the actual value on our calculator and that approximate value using the tangent line approximation is 0.00017. So it's actually an excellent approximation, even with a large step size. And I think the reason why it's an excellent approximation is because the slope is so small at x equals 81. That slope is actually -1/18, or excuse me, +1/18, and then we multiply it by -1. So it gives us an excellent approximation of the square root of 80. And we didn't even have, well, I'd say we didn't have to use a calculator. We did have to use a calculator to approximate 1/18. But we can do all these calculations without a calculator if we want to. But it's nice to have a calculator giving us those decimal approximations. So that's it for our lesson. Our lesson on differentials. We say the linearization of y equals f of x at x naught is just the tangent line, and instead of writing y, we usually write L of x for linearization. When we're talking about a linearization, we're just talking about the tangent line. It's just a linear approximation of the function. That is very closely related to these concepts of the increment of y and the differential of y. The increment of y is the actual change in y as x goes from one value to a neighboring value, as x changes from x naught to x naught plus delta x. The differential of y can be used to give us the expected change in y if we substitute a particular x value at the base point of interest, and that dx would be how much that x changed by. So it'd be the x final minus x initial. So if you substitute a value here and you substitute a value here, this dy has physical meaning. It's the expected change in y using the tangent line approximation, or that distance from there to there. And we want to compare that to the actual change in y, just using the function values at those 2 points. And they're going to be very similar as long as that delta x or dx is very small. Now, there are some problems with this. Typically, dx is used for an infinitesimal and delta x is used for a finite change in x. In this section, we use dx and delta x interchangeably. Now, delta y and dy are not interchangeable because y depends on x. So delta y is an actual difference in y values. Dy is an approximate change in y values. It's an actual change in y values on the tangent line, but it's an estimate of the change in y values on the original function. So those are the 3 types of problems we'll do. We'll compare the actual change to the expected change using the tangent line approximation. We'll look at propagated error problems. We might be asked to compute relative error and percent error so that we have a sense of how large that error is compared to some measured value, or not just measured, but calculated value, and that calculated value is using the measured values. A calculated value was calculated using measured values, excuse me. And then estimating values like the square root of 80, for example, without a calculator. We know the square root of 80 is very closely related to that square root of 81. So we take the original square root of 81, and then we add the change in y that's expected using the tangent line approximation to get an approximation of the square root of 80. And we found out that it was pretty good. The error was less than 0.001, which is very small. We didn't do relative error on this one, but we could have if we wanted to. I think we have one more lesson in the chapter on applications of differentiation, and that's L'Hopital's rule. It's going to allow us to find limits of functions when we have a 0 over 0 indeterminate form, or an infinity over infinity indeterminate form, plus or minus infinity over infinity. And then I think we'll be done with our applications of differentiation section, and we'll be happy to move on to anti-differentiation and integration, which is how we finish the course.